Okay. Good morning. I'm Ted Fisher. I'm from Rochester Hills, Michigan, and I'm going to talk about SMLs this morning. Fourth time's the charm. Okay. What I want to show you here on the opening page is these are my two SMLs. This is a 42-inch loop, and it works 17, 20, and 30 meters. And this is my 6-meter loop. This will actually fit through a basketball hoop. And I use it for 6-meter sporadic E-layer work in the June and July timeframe. And the thing I want to really point out about these SMLs is this is how they operate on top of a tripod. No tower, no elevation. They just sit on a tripod in my garage and they do their thing. So as I realize now from breakfast, most people know what an SML is. So it's a resonant antenna that trades bandwidth and efficiency for compact size and portability. Mine have three main pieces to it. They have a tuning box, which I have here on the table so you can look at it. There's a main loop, and then there's a drive loop, which is the exciter for the system. Not all SMLs have drive loops. You can also use a gamma match or other ways to attach to drive the main loop, but I find this very useful for minimizing the SWRs. I'll point out in another slide or two. The challenge they have, low radiating efficiency and very sensitive tuning. It's a compromised antenna. It's never going to be as good as a full-size antenna, but in some cases and in some situations, it's good enough. And that's the main thing. You can use it for base or portable, for CW phone or data, but it is best suited for situations where you're going to do a lot of QSOs at a single frequency setting, just because it's such a challenge to change the frequency. So if you're using, as I do, the modern digital modes, the FT8 and the JS8, on each band there's a particular frequency. Right, on 20 meters, FT8's 14.074. All conversations take place on 14.074. So you can set it once there in the morning and you can make QSOs all day long on 20 meters. The other place you'll see them used, and they show up on the, sometimes on the cover of QST magazine, is when somebody's activating a peak, activating a summit, or activating a park, because in that case, you're the call magnet, the calls are coming to you. So you set your frequency, you set call CQ and just sit there and handle the calls. What you can't really do very well with these is scan the band. It's difficult at best. So as I said, my experience I'm going to talk about is mostly with the digital modes, but there's been talk about, you know, somebody here saying they really can't hang an antenna outside because of homeowners covenants and so forth. These are good stealth antennas. Mine are built out of PVC, on a PVC frame, which is pretty fragile. So I don't take them outside except in fair weather at best. So all the results you're going to see here later on were all done from in my garage. I've got 100 feet of coax that runs out the garage door, along the base of the house, back into the house, and then into my radio room. And all the antenna works out there in the garage. I'll just mention, it doesn't seem to matter whether the garage door is open or not. And they operate without degradation, as far as I can tell, when they're about a loop diameter away from my Prius that's parked in the car in the garage. So they seem pretty immune to local effects. This is a schematic of my 42-inch loop. The main loop is 42-inch diameter loop of LMR 400 coax. Only the shield is connected. The shield is the radiating element. There's no connection to the center conductor. I like the LMR 400 because it has a solid center conductor. So it tends to stay in a circular loop if you make it into a circular loop. If you put something up with like an RG8X, it's sort of a limp noodle, it just collapses. So you have to find a way to hold it up. But if you use a solid center conductor, it helps. It's a big help. Drive loop, that's a number 14, number 12, number 10, depends on what I have at hand at the time, bare copper wire, and it magnetically couples into the main loop. That's where the excitation takes place. At the bottom of the loop is the tuning capacitor which is typically my variable capacitor. Whoop, sorry about that. Typically my variable capacitor that I brought along. I use that on all the different HF loops, and a fixed capacitor in parallel, which is band specific. And I'll get to why that's a good idea later, but the fundamental purpose is it makes the variable capacitor a trimmer, a fine tune, and it makes it a whole lot easier to tune when most of the capacitance you need is in the form of a fixed capacitor hanging underneath of that. Just makes life a lot easier. High voltage alert, serious high voltage alert. Despite their simplistic, innocent look, SMLs generate fairly high voltage on the tuning capacitor. The calculations at least show that the 42-inch loop that I like to run will generate about 1,000 volts peak, a little better than that, at 20 watts, and something close to 2,500 or more at 50 watts. And while I don't have a way to measure that voltage, I'm going to show you a picture in a minute which convinced me that it's really there. So when you're running this, you want to make sure nobody can make contact with the ends of the loop or the tuning capacitor. This picture right here is my little 6-meter SML lighting up a fluorescent tube. There's no connection to the tube. It's just suspended there near the antenna. But the little SML, when I'm transmitting, really lights it up. So there are serious fields, electric fields present there. The main, a vertical SML loop, the main loop, if it's vertical, it radiates a vertically polarized signal. It also radiates out the side of the loop, not the face. The first one I bought, I was ready to work stations east and west. I turned the loop to face east and west and got almost nothing. So I called up Steve at Alpha Antenna, and Steve explained to me, no, it's out the side of the loop. You got to turn it. So if you want to work east and west, you want your loop facing north and south. Not necessarily obvious to me, at least, but that's the way they work. Now, the standard guidance is that the circumferential length of the loop should be somewhere between 0.1 and 0.2 wavelengths. So that means that this is really a compact antenna. I'm not sure what the half wavelength is at 20 meters, but it's I don't know, it's big, right? 30 feet, something like that. So when you're getting 20 meters out of this thing and it's only 42 inches in diameter, you've really shrunk down the size of the antenna. And the effect of that is that the radiation resistance, instead of being 72 ohms like an ideal dipole or 120 for a quad or something, it's down to 30 to 300 milliohms. Very, very small. Now, that wouldn't be a problem, except that the equivalent loss resistance in series with it, the resistance that accounts for all the losses, the ohmic losses in the loop, all the joints, there's some loss in the capacitor because the plates aren't welded and so forth, tends to be a lot bigger than that, anywhere from half an ohm to an ohm and a half. And so it swamps out the radiation resistance, and you end up with radiating efficiencies in the 5 to 20% range. Not much, but again, under the right circumstances, it's enough, and you can do good things with it. Technical overview. Here are the bandwidths that I get out of my loops. It varies from the 42-inch loop. It varies from 50 kilohertz to 150 kilohertz at 17 meters. I'm very disappointed in these numbers. I don't know why they're so broad, the bandwidths. I expected no more than half that. So I've got some extra losses in the loop that either because of the connectors I'm using or the fact that I'm even using connectors instead of having hard joints. But I have a lossy loop and it spreads out the bandwidth. Now, something else I discovered early on, and then I've read it since then, but not in many places, for an SML like mine, which uses a drive loop. To minimize the SWR, what you need to do is adjust the mutual inductance between the smaller drive loop and the larger main loop. You can do that in a number of ways. In the 42-inch loop that I've got here, I turn the drive loop into or out of the plane of the main loop to change the mutual inductance. On the 6-meter antenna, it's got a little drive loop up here. I grab it and I just tilt it in or out to adjust the SWR. If you do that, you can get an SWR at one frequency that's almost always smaller than 1.1 to 1. And I think that's important because I don't want any more reflected power than I can possibly do without, because I'm having enough trouble getting power going out of the antenna. So I don't want to waste any of it. So you've got to be able to adjust that drive loop either by tilting it or turning it or sliding it, but you need to be able to adjust that to minimize the SWR. And the optimal, the optimal position of the drive loop depends entirely on the losses of the antenna. I've seen that in experience. I've derived that analytically. It's a true statement. So when the losses change as you go up in band or down in band, you need to adjust that mutual inductance again. They're easy to build. There's not much to them except for the capacitor. That's the bugaboo in the whole thing. If you want to operate at 20 watts, sorry about that, I'll get to that in a minute. If you want to operate at 20 watts, you probably need a capacitor that's rated at 1500 volts. If you want to go to 50 watts, you probably need 2500. Butterfly capacitors and split stators are preferred because otherwise you have a variable capacitor that has a rotary joint in there, right? So there's a spring-loaded contact that's pushing against maybe the shaft that the rotating plates are on. That joint, which is an all receiver variable capacitors, was never intended to carry 3 to 5 amps of RF current. If you persist in doing it, as I did at one point, the joint will get very lossy and then it will fail. And when it's lossy, it will be lossy in a nonlinear way. So if you're going to go above 20 watts, you really need either a butterfly or a split stator. That's a split stator capacitor there. I mean, it has 2 independent sets of stator plates and a common set of rotor plates that go in and out. And this is a schematic of it. And in its original use, one side of a balanced line connected to stator plate 1 and the other one to stator plate 2. And this center, this is the rotary joint here. And the rotary joint was then tied to ground. And so you could change the capacitive loading on the balanced line, and you could do it in unison with both sides. I just don't use this. You don't connect this. So if you don't connect this and there's no current flowing through the joint, you have pretty much the equivalent of a butterfly capacitor, except that you are piping RF current up and down the shaft that connects the rotary plates. So there is some extra loss that gets picked up there.
So
yeah.
Bruce is asking, what is the typical value of a capacitor like that?
This one is 9 to 29 picofarads. And I'm going to come back to that in a minute. That's a relatively small amount of capacitance. On the 42-inch loop, I think at 30 meters, where the frequency is as low as I go, and so I need as much capacitance as I can get, I really need about 75 picofarads to tune it. So I hang maybe 70 picofarads on that as a fixed capacitance, and then do plus or minus 5 around the center point as the fine tuning. But I'll revisit that. Thanks for asking that. That's 75 picofarads is about right for 30 meters, and you can scale it up and down from there. I also recommend for tuning it that you get yourself an antenna analyzer with a sweep capability. I know Mike Sharp here mentioned there's a brand out there, or several brands now that are under $100. You can get is it the nanos? Yeah. It really, if you're going to play with SMLs, it's a big help to have that. Here are some SMLs I have known and loved and built. This is my first one up here on the left. It's a modified alpha antenna. It used to be called the Alpha Senior Loop. Bought it in 2015, started modifying it in about 3 months. It's a backpack. It was advertised as a backpacker SML because the main loop is pre-shaped aluminum straps that get screwed together with a screw and a nut. I added an extra doghouse here and put a small capacitor here, and an 8-to-1 drive on the main, so that this became the bulk tuning and this became the fine tuning. And you almost can't see it, but there's a copper loop right here, which replaced the fixed aluminum strap. I apologize, this is sensitive to touch. Replaced the aluminum strap, which you really couldn't move. This copper loop up here will easily tilt in and out, and you can minimize the SWR to something close to 1-to-1. This is my XSML, was originally meant to be in my experimental SML. What this is, and I'm going to show you another picture of it later, this is a 42-inch loop twisted into a figure 8, and then the top folded down to the bottom. So this antenna is the same as the 42-inch loop I showed you on the opening page. It's just been compressed. And it makes a really neat package because each of these loops now is 21 inches in diameter, pretty compact. Did it work? Well, yes and no. It worked. There's no question about it. In my top 20 distant contacts, it comes in at number 18. So it works. But I gave up something, and I'm still trying to figure out how much I gave up. I think I gave up about 25 to 30% of the efficiency relative to what it was originally. So anyway, and here again, here's the same tuner box down here at the bottom of the loop. And in the back is a drive loop on a bracket that rotates. This is this close-up of the 6-meter loop. Here again, this is the drive loop, and it tilts in and out. And I'm going to talk about this pigtail hanging down here in another slide or two. This is my dual loop. This is my current favorite. This is 2 parallel loops, not series, parallel. The idea was to cut down on the loss resistance and maintain the same radiation resistance. It's worked real well for me. This is a blow up of down at the tuning box. And again, same tuning box here and here and here. And once you get a tuning box, you can do a lot of projects with it once you get one built. Here, the 2 loops come down, they're joined together, and they feed one set of plates, and then here's the other side feeding the other set of stator plates. Again, only the shield is connected, no connection to the center.
Maybe you could point at the screen, because we're not seeing the cursor on the...
Oh, you're not? Oh.
Unfortunately, and if it goes on recording, we won't be able to...
Oh. All right. Yes. Okay. Let's show up on here. No. Okay. Not going to use that. All right. Let me point out here. What I was saying here is that what you see with the capacitor tuning assembly that I brought, it's here on the XSML. A smaller version of it's down here on the 6-meter. Over here is the detail of where these 2 loops, which are to the maximum extent that I can make them the same. This is where they come into the tuning box, and they're joined. And again, there's no connection to the center conductor. And this is really useful. Now, this is from the 42-inch loop. The what you do is you put the drive loop on a rotatable bracket. And it rotates about the vertical support for the main loop. You put a protractor scale on the bracket, and you put a fixed pointer attached to the frame of the antenna. And now you can, when you get the SWR minimized, you can read the angle on the protractor scale. And now when you come back and want to work that same band again, you know roughly where to set the drive loop. The protractor scale will show you. We still on?
Does this help using this?
I have it,
Oh,
Yeah.
you could see what it was doing?
more or less.
Okay. All right, so what I want to show you here is the 42-inch loop working at 50 watts. This is FT8 on 30 meters. And this is the decode range that I got from PSK Reporter. And as you can see, it goes up to Alaska, down to the northern tip of South America, well into Europe, up to Finland. And that's from a 42-inch loop running 50 watts. So it doesn't radiate as well as a full-size antenna, but it does the trick for making contacts. Again, this is another view of the SML, the double loop that's made by twisting the 42 and figure 8 and doubling it up. And then here's a blow up of the protractor scale and the fixed pointer in order to record and then reset the drive loop. Now, voltages. The center picture is a hole blown through two 600 volt Teflon insulated wires. So those wires are supposed to be rated at 600 volts, which means they're tested, as I understand it, at 600 plus 1,000. So the two together ought to be theoretically good for 3,200. All right, you won't get that, but maybe you get 80% of it. Blew a hole right through it. Now, I think this happened when I accidentally overdrove the loop. I don't have good notes for when this occurred, but there was a time when I think I had the power set way too high and keyed the transmitter and blew out the wires. But the point is, there's enough high voltage there to blast through these two wires. So it's real. I have no way to measure it. I've also blown through a piece of LMR 400 coax that I was using as an antenna, and that's supposed to be good for 1,500, and I blew a hole right through it. So there's serious voltage in this thing. When it's transmitting, it doesn't hold any of the voltage because the main loop is essentially a shorting bar between the two capacitor terminals. So there's no danger in it holding charge, but when it's transmitting, it produces a lot of voltage. If anybody in here has seen a demonstration of a relatively large Tesla coil where they shoot lightning bolts that are 6 or 8, 10 feet long, that's a resonant circuit. And that's what resonant circuits can do. So there's real voltage here. Please be careful. What can you expect to get? Here you go. This is my top 10 list for digital contacts. And the type of loop is listed over on the right. Over on the left is the date and then the call sign, and in the center is the power. These are all done on FT8 except the one that's JT65. And I got lucky one day. I actually got a confirmed contact in Japan from my 36-inch SML. Now, you notice it says braid. The whole trick, the holy grail for making an SML is to maximize or minimize the resistance of the main loop. Now that means the conducting material, it means all the joints, it means the capacitor. In this case, I had a 36-inch SML made out of coax, again, only connecting to the shield. It was working pretty well. I decided to try an experiment, so I bought some 1-inch woven copper braid, like you would put over a wiring harness. So it's 1 inch in diameter. It's woven tinned copper braid, and I just slid it over the 36-inch loop and connected the ends of the braid instead of the coax to the tuning capacitor. And it really, really works. It worked well. And if you think about the way the equations go, the loss resistance, the ohmic resistance, the AC ohmic resistance decreases as 1 over the diameter. So in this case, I went from a 0.32 shield, 0.32 inch shield, to a 1 inch. So it's about a 3-to-1 increase in diameter. It's about a 3-to-1 decrease in the ohmic losses. And as you can see, a braided SML took 5 of the 10 top places. Now, the problem is it's hard to hold up. It is heavy, very, very heavy. But again, it shows, perhaps more than anything else, it shows the impact of trying to manage that loop resistance to get it as small as you can, the loss resistance. Now, most people aren't going to run a 50-watt loop to start with because you just can't find capacitors like that everywhere. So here's what you can do with 20 watts. This is my top 20. All of these, except this one 142-incher, all of these were made with the modified alpha. That's the first one I bought back in 2015, and then I worked with it some. And I don't know if people recognize JT9 and JT65. Those were the original Joe Taylor weak signal. It took 6 minutes to complete a QSO, as opposed to 90 seconds. Anyway, the reason all of this happened, or most of it happened in 2017, is that after 2017, I had that capacitor, and I never worked 20 watts again. I just went upscale. But this is what you can do with 20 watts, and it's a pretty good spread. You can certainly work Europe on it. So no problem there. Build considerations. I think I've probably talked enough about the voltages and so forth, but somebody asked about, how much capacity does that have? It's 9 to 25 picofarads. What I love to do, what I think is absolutely the greatest way to do it, is to hang a couple of fixed capacitors. Oh, I'm sorry. I keep thinking I can see the cursor. There are things called doorknob transmitting capacitors, RF parts, and Nebraska surplus supply, I think, sells them and other things. These are, I don't know what I'm going to guess, these are probably a 50 or 25 picofarad cap. The point is they're rated 5 kilovolts and they'll take 5 to 10 amps. So that's what you need for the fix. And you hang those, in this case, I hang them down below the tuning capacitor, and these have leads that come up and connect to here and to there. So they are across the loop in parallel with the 9 to 29 picofarad tuning. That makes this the fine tuning capacitance. And this supplies the bulk of the capacitance. When I do that, I've got 9 to 29 picofarads here, so the variability is about 20 picofarads. I'm driving it with an 8 to 1 Fillmore S38 reduction drive here. That's labeled 0 to 100. So each tick on this mark is 0.2 picofarads. And sometimes to get resonance, the difference between off resonance and on resonance is 1 tick. So really touchy. So this is a good way to do it, though. It's a bit of a burden because you got to change out the bulk capacitors each time you change bands, and it really makes it a lot easier to. Okay. What else do we have? Oh yeah, the other way to make some additional bulk capacitance, fixed capacitance, is to either use an open-end piece of coax. It's about 24 picofarads per foot, but it's also probably going to only be rated for about 1500 volts. So you can do 20 watts on it. That'll make a good capacitor. If you need 12 picofarads, cut off 8 inches of coax, and you got it. But you want to stop the shield and then extend the center insulating dielectric and then terminate the shield here. You want some arc length between the exposed end of the center conductor and where the shield stops. If you just, cut them off together, it'll arc right across the end. So this dielectric has to be extended. The other way to do it is to buy some PTFE, Teflon insulated wire, 600 volt. I just checked before I put this together. It's still available on eBay, $10 for 10 feet, I think it is. Put it, put 2 wires in parallel, clamp on a vise, put it in a drill, right? You got a twisted pair. And down at the end, you splay that, the open end, you splay that so it doesn't arc across the end. Hook it up. And the nice part about that is you find if you have a little too much capacitance, you just start untwisting it. That's about, about a picofarad for every twist you remove or put back on. So you can do it that way. So those are 2 good ways to add fixed capacitance in parallel with your tuning capacitor. And I like to put a clamp on ferrite core at the top of the twisted pair, just so I don't have any common mode current flowing. I wouldn't use house wire. I did, and it doesn't work very well. The problem is the nylon is very lossy at high frequencies, and particularly in a high voltage field. And so it drives up the SWR. Not only drives it up, but you can watch it drive it up. So the first one I made out of number 12 house wire and keyed the capacitor. I was working FT8. I started out with an SWR of 1 and 1.5 and 2 and 2.5 and 3. And at that point I pulled the plug. I don't know where it was going, but clearly the nylon was heating up or something and its characteristics were changing. So house wire doesn't work really well for that. And here's my S38 Fillmore. These are about $35. It's a little pricey, but it's worth it. And now you can tweak in fractional picofarads, which is sometimes what it takes to optimize it. Main loop, there's not much to say here, except that the thing you're trying to minimize is the surface resistance of the main loop, because it's the nature of RF current that it flows on the surface of the conductor. Now, it doesn't really all stay on the surface, but it only penetrates about 2 or 3 mils, 2 or 3 thousandths of an inch into the conductor. So hollow conductors are fine. And I know there are guys who build, because it's what they can get, they got 7/8, I think it's air conditioning tubing or something, 7/8 copper that'll bend and you can make into all the material in that loop below 2 or 3 mils from the surface is doing nothing except adding weight. It's just weighing down the antenna. So what SML builders would love to find, and I haven't been able to find it yet, is plastic tubing, bendable but not a limp noodle, with about a 5 mil conductive coating plated on it. That would be the ideal SML main loop, but I don't know where to get something like that. And the drive loop, not much to say here. I've already spoken a lot about it, but the standard guidance is 20%. I guess I build lossy SML, so I make mine 30 or 35%, which would be too much mutual inductance if I had to stick it in the plane of the main loop, but I don't, because I put that in and then I rotate it relative to the main loop until I get what I need, and that brings the SWR down to 1.1 or less. And in the end, I get a nice 50 ohm input. I don't need to walk through these, but they are in the package, and Mike has it. These are the analysis equations for a loop. And it's from a website put up by AA5TB. I looked him up once, but I don't remember who he is. Claims are from the 1988 edition of the ARRL handbook. I don't know that for a fact, because if I knew that for a fact, then they might be copyrighted. So it's just a claim that that's where they came from. So they're here. The algebra is a little ambiguous at places. So you can probably figure everything out, but there's one particular one. Oh, here, this is the voltage on the capacitor, and it's an RMS, is the square root of, and then this parenthetical expression power times the reactance of the inductance times the Q of the antenna. You can't really tell, but all that is inside the square root. It's a little ambiguous. It's not really quite meticulously written. I don't know why he threw this line in. This is what this really amounts to, is that in dry air between flat plates with no burrs, everything's cool, smooth edges, you can get about 3,000 volts per millimeter of gap. So that's where this came from. This table shows the effect of applying those equations to my 42-inch loop. So here are the results for 17, 20, and 30 meters. Two things you can see as the frequency goes up. So here we go from 30 up to 17. We're going from about 10 megahertz up to 18. The voltage of the capacitor goes up from 876, and this is RMS volts, so the peak is another 40% on top of it, from 876 up to 952. At the same time, the current through the capacitor, so this would be through split between the variable capacitor and the doorknob transmitting capacitors that are adding the bulk capacitance, decreases from about 4 amps down to about 2.5. So if you want to try out the equations and check to see that you're doing them right, you can take any set of numbers here and plug them in, and you should get the same thing I got. And finally, just to make sure there's no ambiguity in how to interpret the equations, this is from Mathematica. It's a program I use to do my calculations, but it's the same set of equations, but I think it's unambiguous in terms of what terms are grouped together. So this would be, if you were going to program an SML analysis program in BASIC or something, this is what it'd look a lot like this. Except Mathematica has this strange notation where this term means 3.38 times 10 to the minus 8. It's a little unusual. That's it. Any questions? All done. Ready to go build. It's good. Now, I'll throw in one gratuitous comment. This should work. I've built this once, but I never transmitted on it. But I did receive on it, so I know it works. Get yourself a piece of coax that you can form into a loop. Make the loop, terminate it on a piece of wood or something. Just hold everything in place. Figure out how much capacitance you need. Take all of that minus 10 picofarads, 20 picofarads, something like that. Cut another piece of coax, snip it off, make sure you got the center insulation extended, cut it off. There's your bulk capacitance. Invest $10 in some Teflon wire from eBay. Twist up a capacitor, hook it in parallel with the coax. Put your antenna analyzer on it and start tuning by untwisting the wires. And when you find, and you gotta have a drive loop to adjust. And when you get all done, you should have an SML with nothing but wire. There's no capacitor in it, no discrete capacitor anywhere. It's an all-wire SML. And it costs a fraction of $10, but you got to buy the Teflon wire. I know it works for receiving. I have in my logbook the stations I received on it. I can't find anything in my logbook that says I transmitted on it, but I can't believe I got that far and didn't key it up. But I don't have a record of it. So if you want to play with one of these, you can probably make one for about $10 and see what happens. Okay, that's it. Thank you.